Our galaxy has a neighbor twice our size. Right now, it's racing toward us at incredible speed. Most people think galactic collisions mean stars smashing into each other. That's completely wrong. Tonight we're discovering what this cosmic giant actually looks like, and why our inevitable meeting will change everything we know about our cosmic home. Before we dive into this approaching neighbor, drop a comment about what you imagine when you hear galactic collision. If these cosmic journeys fascinate you, consider subscribing. These discoveries are meant to spark wonder together. For decades, astronomers couldn't believe what they were measuring. This neighboring galaxy stretches farther than our wildest estimates. Way farther. Andromeda spans a distance that light takes 200,000 years to cross. Our own galaxy barely reaches half that size. When you scale it down, Andromeda becomes the massive shopping mall next to our neighborhood grocery store. Scientists call this a galactic disk. That's the flat, spinning structure that contains most of a galaxy's stars and gas. Andromeda's disk dwarfs ours completely. What's remarkable is how something this massive holds together at all. Gravity operates across these impossible distances with perfect precision. Every part of this galactic giant rotates in harmony despite spanning more space than human minds can grasp. Stars don't just fill space randomly in Andromeda. They organize into the largest community the universe offers. Each star burns with nuclear fire that could power civilizations for billions of years. Inside this galaxy, more stars exist than every grain of sand on every beach on Earth combined. That number sounds impossible. 1 trillion individual stars, each one a blazing nuclear furnace. The galaxy's center glows with ancient red giants. These are massive stars near the end of their lives. They've swollen to enormous sizes and burn with reddish light. Millions of them cluster together in Andromeda's heart. Throughout the spiral arms, young blue stars blaze like cosmic streetlights. These stellar babies burn so hot they appear blue-white. They mark the neighborhoods where new stars continue forming from cosmic gas and dust. This trillion-star empire maintains perfect gravitational order across impossible distances. Mass means everything in space. The more massive something is, the stronger its gravitational pull. Andromeda doesn't just look bigger than our galaxy. It actually contains more stuff. Scientists estimate Andromeda's total mass at about 1.5 times our Milky Way. That includes all the stars, gas, dust, and invisible dark matter. This extra mass gives Andromeda tremendous gravitational power over its cosmic neighborhood. What's shocking is how much of this mass we can't see. Stars and gas make up only a small fraction of any galaxy's total weight. The rest comes from dark matter, invisible material that doesn't shine but still pulls on everything else through gravity. For Andromeda, this massive gravitational presence has shaped its structure over billions of years. It holds those trillion stars in perfect orbital patterns. It captures smaller galaxies that wander too close. This extra mass explains why Andromeda dominates the cosmic real estate around our galaxy. Space contains vast emptiness between galaxies. Most galaxies sit so far away that their light takes billions of years to reach us. Andromeda breaks that pattern completely. This cosmic neighbor sits just 2.5 million light-years from Earth. That might sound incredibly far, but it's practically next door by galactic standards. Light from Andromeda's stars takes that long to travel through empty space and reach our telescopes. Scientists call Andromeda the nearest large spiral galaxy to our own. That's important because most galaxies visible in our telescopes are much smaller dwarf galaxies or incredibly distant giants we can barely make out. For astronomers, Andromeda's closeness offers an incredible opportunity. We can study individual stars, gas clouds, and stellar neighborhoods in detail that's impossible with more distant galaxies. This proximity lets us see how large galaxies actually work from the inside out. Brightness in space comes from all those burning stars added together. The more stars a galaxy contains, the brighter it appears in our telescopes. Andromeda creates one of the most brilliant displays in our cosmic neighborhood. Combined light from all of Andromeda's stars equals about 25 billion times our sun's brightness. That represents the power output from 1 trillion individual stellar furnaces all burning at once. What makes this even more remarkable is that we're seeing Andromeda edge on from our perspective. We're looking at the galaxy from the side, not face on. This angle actually reduces how much light reaches us compared to if we saw the galaxy's full spiral face. For comparison, our own galaxy produces similar amounts of light, but Andromeda's larger size and greater star count give it the edge. This incredible brightness makes Andromeda visible to naked eye observers on dark nights as a faint smudge in our sky. Galaxies don't just scatter stars randomly through space. They organize stellar populations into beautiful patterns called spiral arms. Andromeda displays this cosmic architecture on a massive scale. 2 major spiral arms sweep outward from Andromeda's center like enormous cosmic pinwheels. These aren't solid structures. They're regions where stars cluster more densely than in surrounding areas. Scientists call these density waves. That's when material gets compressed as it moves through certain regions of the galaxy. Gas clouds collide and compress in these spiral zones, triggering bursts of new star formation. What's fascinating is how these spiral patterns maintain their shape over billions of years. Stars orbit the galaxy at different speeds depending on their distance from the center. Yet somehow the spiral structure persists despite this differential rotation. The spiral arms serve as stellar highways that organize galactic traffic across cosmic distances. What you can't see controls what you can. Around Andromeda's visible disk extends a massive sphere of invisible material called dark matter. This unseen empire dwarfs the galaxy we actually observe. Dark matter doesn't emit light or interact with normal matter except through gravity. Scientists know it exists because of how it affects the motion of stars and gas throughout the galaxy. Without this invisible scaffolding, galaxies like Andromeda couldn't exist. This dark matter halo extends far beyond Andromeda's visible edges. It probably reaches several times farther out than the spiral disk we see in photographs. The entire visible galaxy sits embedded within this invisible gravitational structure. For Andromeda, dark matter provides the gravitational foundation that holds everything together. It keeps the outer regions of the galaxy rotating at proper speeds. It captures and organizes the smaller satellite galaxies that orbit Andromeda like cosmic moons. This invisible empire shapes everything we can observe about our galactic neighbor. At Andromeda's center sits a crowded stellar metropolis. Billions of old stars packed together in a football-shaped region astronomers call the central bulge. This cosmic downtown glows with golden light. These stars formed billions of years ago when the galaxy was young. They've aged into red giant phase, swelling to enormous sizes and burning with reddish-yellow light. When you see millions of them clustered together, they create that characteristic golden glow. The central bulge contains some of the galaxy's most massive stars. They've had time to accumulate heavy elements from previous generations of stars that lived, died, and scattered their contents back into space. What's remarkable is how densely packed this region becomes. Stars in Andromeda's bulge sit much closer together than in our galactic neighborhood. If Earth orbited a star in that central region, our night sky would blaze with thousands of bright stars instead of the few thousand we see now. Right now, Andromeda spins through space at speeds that dwarf anything on Earth. The entire galaxy rotates like an enormous cosmic pinwheel, carrying its trillion stars along for the ride. At its fastest regions, material in Andromeda moves at roughly 1 million kilometers per hour. That's fast enough to circle Earth's equator in about 4 minutes. Yet this incredible speed represents the stately, measured rotation of a galactic system. Scientists call this differential rotation. Different parts of the galaxy rotate at different speeds, just like a whirlpool in water. Inner regions complete orbits faster than outer regions, but the overall pattern remains stable. For such a massive structure to maintain this rotational harmony requires incredible gravitational precision. Every star, gas cloud, and dust particle follows orbital mechanics on a scale that makes planetary systems look tiny. This spinning motion has continued for billions of years and will continue for billions more. Andromeda doesn't exist alone in space. Dozens of smaller galaxies orbit around it like cosmic moons. These satellite galaxies form a gravitational family system on an enormous scale. The largest of these companions include galaxies with names like M32 and M110. These are much smaller than Andromeda itself, but still contain millions or billions of stars each. They follow elliptical orbits around the main galaxy. Scientists call these dwarf galaxies because of their small size compared to giants like Andromeda. Most contain old, reddish stars and very little gas for forming new stars. Andromeda's powerful gravity has stripped away much of their material over cosmic time. What's fascinating is how this satellite system resembles a scaled-up version of our solar system. Just as planets orbit our sun, these dwarf galaxies orbit Andromeda. The gravitational relationships work the same way, just on scales millions of times larger. This galactic family demonstrates how gravity organizes matter at every level of the universe. In our corner of the universe, only 2 galaxies really matter. Andromeda and our Milky Way dominate what astronomers call the local group, our cosmic neighborhood extending across millions of light years. The local group contains about 50 galaxies total, but most are tiny dwarf galaxies with only millions of stars each. Andromeda and the Milky Way outweigh all the others combined by enormous margins. These 2 galactic giants control the gravitational dynamics of our entire cosmic region. Smaller galaxies either orbit one of the 2 giants or drift through the space between them. Nothing else in our local universe comes close to their mass and influence. What makes this cosmic arrangement even more significant is that Andromeda and our galaxy are approaching each other. In about 4.5 billion years, these 2 gravitational titans will merge into a single, even larger galaxy. This future collision will reshape our entire cosmic neighborhood and create the dominant galaxy in our local universe. Look at any spiral galaxy and you'll see beautiful curved arms sweeping through space. Most people think these arms are solid structures made of stars. That's completely wrong. These spiral patterns aren't permanent fixtures. They're waves. Scientists call them density waves, regions where material gets compressed as it moves through the galaxy. Think of traffic on a busy highway. Cars bunch up in certain areas, then spread out again. The traffic jam itself moves along the road, even though individual cars pass through it. Spiral arms work exactly the same way. In Andromeda, These density waves sweep around the galaxy at different speeds than the stars themselves. As gas clouds encounter these compression zones, they get squeezed together. This compression triggers bursts of star formation that light up the spiral pattern we observe. Space appears mostly dark and empty to our eyes, but scattered throughout Andromeda's spiral arms, brilliant pink clouds blaze with the light of stellar nurseries. These glowing regions get their distinctive color from hydrogen gas. When young, hot stars form nearby, they blast the surrounding space with intense ultraviolet radiation. This energy ionizes the hydrogen atoms, stripping away their electrons and making them glow bright pink. Scientists call these H2 regions. That's shorthand for ionized hydrogen zones where the gas has been electrified by nearby stars. The Roman numeral 2 indicates hydrogen with one electron removed. What makes these regions so important is that they mark active star formation. The massive young stars causing all that ionization formed recently from the same gas clouds they're now illuminating. These pink beacons show us exactly where Andromeda continues creating new generations of stars. Cosmic dust blocks our view of what's happening inside Andromeda's spiral arms. These aren't the dust bunnies under your bed. Cosmic dust consists of tiny particles of carbon, silicon, and metals scattered through space. Dark lanes of this material trace along the inner edges of each spiral arm. From our perspective, these dust ribbons appear as dark silhouettes against the brighter background of stars. They create the distinctive contrast that makes spiral patterns so visible in photographs. The dust accumulates in these locations because of how density waves work. As gas and dust encounter the compression zones, the heavier dust particles get concentrated more than the lighter gas. This creates dense dust lanes that absorb and scatter starlight. For astronomers, these dust lanes present both a problem and an opportunity. They hide much of the star formation happening behind them, but they also mark exactly where new stars are most likely to form. The dust provides raw material for future stellar generations while temporarily hiding the process from view. Inside Andromeda, a stellar factory operates on an incredible scale. This galactic manufacturing process creates new stars continuously, year after year, without ever stopping. Astronomers measure this process as the star formation rate, how much stellar mass gets created annually. In Andromeda, this rate equals roughly 1 solar mass per year. That means every year, the galaxy produces new stars with the combined mass of our Sun. This might not sound like much until you consider the timescales involved. Over millions of years, this steady production creates entire stellar neighborhoods. Over billions of years, it has produced the trillion stars we see today. What keeps this stellar assembly line running is the constant supply of raw materials. Gas clouds throughout the galaxy continue providing fuel for new star formation. Andromeda's spiral density waves keep compressing this gas into the high densities needed to trigger gravitational collapse and stellar birth. Where do stars actually come from? The answer lies in the coldest, darkest regions of Andromeda's spiral arms. Giant molecular clouds drift through the galaxy like cosmic icebergs. These clouds contain mostly hydrogen molecules, 2 hydrogen atoms bonded together, kept incredibly cold by the vacuum of space. Temperatures drop to just a few degrees above absolute zero. Scientists call these stellar nurseries because they provide the raw material for star formation. When density waves compress these cold clouds, gravity takes over. Parts of the cloud begin collapsing under their own weight. As material falls inward, it heats up and starts spinning faster. Eventually, the center gets hot and dense enough to ignite nuclear fusion. a new star is born, often surrounded by leftover material that can form planets. This process transforms cold, invisible gas into blazing stellar furnaces that will burn for billions of years. Scattered throughout Andromeda's spiral arms, groups of the most massive stars in the galaxy blaze with blue-white light. These stellar monsters outshine hundreds of ordinary stars combined. Astronomers call these groupings OB associations. The letters refer to spectral classes, categories that describe a star's temperature and color. O and B type stars are the hottest, most massive, and brightest stars the universe produces. These blue giants form together in clusters from the same molecular clouds. They're so massive that they burn their nuclear fuel at incredible rates. While our sun will shine for about 10 billion years, these giants exhaust their fuel in just millions of years. What makes OB associations so important is their role as cosmic lighthouses. Their intense radiation ionizes surrounding gas clouds, creates those pink H2 regions, and helps trigger further star formation nearby. These massive stars serve as the primary architects of galactic structure, even though their lives burn out relatively quickly. When the most massive stars die, they don't fade quietly. They explode with the force of billions of atomic bombs, creating shock waves that ripple through space for thousands of years. These supernova explosions blast material outward at thousands of kilometers per second. When this high-speed debris crashes into nearby gas clouds, it compresses them violently. This compression can trigger new rounds of star formation in regions that might otherwise remain dormant. Scientists call this triggered star formation. One massive star's death becomes the catalyst for dozens or hundreds of new stellar births. It's like cosmic dominoes falling in slow motion across galactic distances. In Andromeda, this process helps explain why star formation often occurs in chains and clusters rather than randomly. Supernova shock waves create feedback loops where stellar death leads to stellar birth. This cycle has been operating throughout the galaxy's history, shaping the patterns we observe today. Not all regions of Andromeda contain the same mix of chemical elements. A subtle but important pattern emerges when astronomers analyze starlight from different parts of the galaxy. Stars near the galactic center contain higher concentrations of heavy elements than stars in the outer regions. Astronomers call these heavy elements metals. Everything heavier than hydrogen and helium in the periodic table. This metallicity gradient tells the story of how galaxies evolve chemically over time. Early generation stars formed from pure hydrogen and helium left over from the Big Bang. When these stars died, they scattered heavier elements into space. In Andromeda, this chemical enrichment happened most efficiently near the center, where star formation rates were highest. Outer regions received fewer heavy elements because fewer massive stars formed there. This gradient provides a fossil record of billions of years of stellar evolution and chemical processing. Take a photograph of Andromeda, and you'll notice something remarkable about the colors. The spiral arms glow blue-white, while the central regions appear distinctly golden yellow. This color difference reveals the ages of stellar populations in different parts of the galaxy. Young, hot stars emit blue light. Old, cooler stars emit reddish light. When you mix millions of stars together, their combined colors tell the story. The blue spiral arms contain active star formation regions where massive young stars dominate the light output. These stellar babies burn hot and bright, giving the arms their characteristic blue tint. The golden center results from billions of older stars that have evolved beyond their youth. These red giants and aging stars create the warm, yellowish glow typical of galaxy cores. This color distribution shows how star formation patterns have shaped Andromeda's appearance over cosmic time. Here's a puzzle that bothered astronomers for decades. Spiral galaxies rotate like pinwheels, but different parts move at different speeds. This should wind up the spiral arms until they disappear completely. The inner parts of Andromeda complete orbits faster than the outer regions. Scientists call this differential rotation. After billions of years, this speed difference should have twisted the spiral pattern beyond recognition. Yet spiral arms persist. The solution lies in how gas behaves differently from stars as it encounters density waves. Gas can speed up, slow down, and change direction much more easily than stars can. In Andromeda, this gas dynamics creates a complex dance between orbital motion and density wave patterns. The gas responds to pressure changes and gravitational forces in ways that help maintain spiral structure. This delicate balance has preserved Andromeda's beautiful spiral pattern throughout its billions-year history. Stars near Andromeda's center move impossibly fast. Their orbital speeds defy everything astronomers expected to find in galactic cores. These stellar residents race around the galactic center at thousands of kilometers per second. That's fast enough to escape most gravitational fields completely. Yet something holds them in tight orbits despite their extreme velocities. Only one explanation fits the observations. An enormously massive object sits at the galaxy's heart, something so dense and powerful that it can bind stars moving at these incredible speeds. The stellar motion provides definitive proof that supermassive black holes exist. Stars don't lie about gravity. Their orbital behavior reveals the presence of an invisible gravitational monster that dominates Andromeda's central region with mathematical precision. How do you weigh something you cannot see? Astronomers use the same method Isaac Newton employed to discover planets. They watch how gravity affects nearby objects. By measuring stellar velocities near Andromeda's center, scientists calculated the central mass that could produce such extreme orbital motion. The result shocked even seasoned researchers. The invisible object contains roughly 100 million solar masses packed into a region smaller than our solar system. That represents more mass than 100 million stars like our Sun concentrated in unimaginably small space. Scientists call this a supermassive black hole, a gravitational well so deep that nothing, not even light, can escape once it falls past the event horizon. This cosmic monster anchors Andromeda's entire galactic structure through its enormous gravitational influence. Black holes themselves emit no light, but the material falling into them creates some of the brightest phenomena in the universe. As gas spirals toward Andromeda's central black hole, friction heats it to millions of degrees. This superheated material glows brilliantly in X-rays, electromagnetic radiation far more energetic than visible light. X-ray telescopes detect this high-energy emission from the black hole's immediate vicinity. The radiation provides a direct signature of material being consumed by the gravitational monster at the galaxy's heart. These X-ray observations reveal when the black hole actively feeds and when it remains dormant. The emission varies over time as the black hole consumes whatever material happens to fall within its gravitational reach. This high-energy glow serves as the black hole's calling card across cosmic distances. Something unusual appears at Andromeda's center when astronomers examine high-resolution images. Instead of a single bright core, they observe two distinct bright regions sitting remarkably close together. This double nucleus structure puzzled scientists for decades. Most galaxies display single, symmetrical central regions. Andromeda's doubled appearance suggests something disrupted the normal galactic architecture. The most likely explanation involves galaxy mergers in Andromeda's past. When two galaxies collide, their central regions can survive as separate structures before eventually combining into a single core. This double nucleus represents fossil evidence of Andromeda's violent formation history. The galaxy we see today assembled from smaller pieces over billions of years, and its central region preserves traces of these ancient cosmic collisions that shaped its current structure. Near Andromeda's central black hole, star formation has essentially stopped. This cosmic dead zone contrasts sharply with the active stellar nurseries found in the galaxy's spiral arms. The black hole creates this stellar desert through a process called feedback. When the black hole feeds actively, it heats surrounding gas to temperatures too high for gravitational collapse into new stars. High-energy radiation and particle winds from the black hole's vicinity blow away the cold gas clouds needed for star formation. This process operates like a cosmic furnace that sterilizes the central region against future stellar birth. The suppression extends across hundreds of light years from the black hole's location. This dead zone explains why galactic centers often appear dominated by old, red stars rather than young, blue stellar populations. The black hole's influence shapes stellar demographics across the entire central region. How far does a supermassive black hole's gravitational control extend? The answer defines what astronomers call the sphere of influence, the region where black hole gravity overpowers all other forces. Within this sphere, stellar orbits become completely dominated by the central black hole rather than the galaxy's overall gravitational field. Stars follow elliptical paths around the black hole, just like planets orbit the Sun. For Andromeda's black hole, this sphere of influence extends several light years from the center. That might sound small compared to galactic scales, but it represents a region larger than the distance between our Sun and its nearest stellar neighbors. Inside this sphere, the black hole operates as the absolute gravitational authority. Its gravity controls stellar motion, gas dynamics, and the overall architecture of the galactic center, with effects that ripple outward to influence the entire galaxy's evolution. Individual stars near Andromeda's center follow predictable orbital paths that reveal the black hole's exact location and mass. These stellar highways provide the most precise measurements of black hole properties available to astronomers. Stars closer to the black hole complete their orbits faster than more distant stars, following the same laws that govern planetary motion in our solar system. By timing these orbital periods, scientists map the gravitational field with extraordinary precision. Some stars follow highly elliptical orbits that carry them close to the black hole during part of their journey, then swing out to greater distances. Others maintain more circular paths at consistent distances from the central monster. These orbital measurements provide the gold standard for black hole mass determination, the mathematical relationship between orbital speed, orbital size, and central mass allows astronomers to weigh black holes with accuracy that rivals laboratory measurements of everyday objects. What does a supermassive black hole eat? The answer includes gas clouds, dust, and occasionally entire stars that venture too close to the gravitational point of no return. Most black hole feeding happens gradually through a process called accretion. Gas from throughout the galactic center slowly spirals inward, forming an accretion disk that feeds material to the black hole over millions of years. Sometimes more dramatic feeding events occur when individual stars pass too close to the black hole. Tidal forces can tear stars apart, creating sudden bursts of high-energy radiation as stellar material gets consumed. The feeding process explains how supermassive black holes grow from smaller seeds into the cosmic monsters we observe today. Over billions of years, steady accretion and occasional stellar meals allow these black holes to accumulate masses equivalent to millions or billions of stars. Andromeda's central black hole wasn't always the quiet giant we observe today. Evidence suggests it once blazed as one of the most luminous objects in the universe. During its active phases, the black hole would have appeared as a quasar, a cosmic lighthouse visible across billions of light years. These episodes occur when black holes consume large amounts of material and convert some of that mass into intense radiation. The transition from active quasar to dormant giant reflects changes in the black hole's food supply. When abundant gas was available, feeding episodes created spectacular light shows. As the central region became depleted, activity declined to current low levels. This dramatic history explains why we observe both active galactic nuclei blazing throughout the distant universe and quiet supermassive black holes in nearby galaxies. The same objects can switch between active and dormant states depending on their cosmic circumstances and available fuel supplies. Surrounding Andromeda's central black hole lies one of the most crowded stellar neighborhoods in the known universe. Millions of old stars pack into a region just a few light years across. This nuclear star cluster contains stellar densities thousands of times higher than in typical galactic regions. Stars sit so close together that gravitational interactions frequently alter their orbits and sometimes eject them from the cluster entirely. Most cluster members are ancient red giants and evolved stars that formed billions of years ago when the galaxy was young. They represent some of the oldest stellar populations in Andromeda's entire structure. The cluster's extreme density creates a unique gravitational environment where stellar collisions and close encounters occur regularly. This cosmic traffic jam demonstrates how supermassive black holes reshape their immediate surroundings through powerful gravitational effects that compress matter to extraordinary densities. Even the hungriest black holes face a fundamental limit on how fast they can consume matter. This cosmic speed limit prevents black holes from growing without bounds. When black holes feed too rapidly, the intense radiation produced by infalling material creates outward pressure that pushes additional matter away. Scientists call this the Eddington limit, the maximum rate at which any object can accrete matter. For Andromeda's black hole, this limit determines the maximum brightness achievable during active feeding episodes. The radiation pressure from rapid accretion eventually chokes off its own fuel supply. This physical constraint explains why supermassive black holes require billions of years to reach their enormous masses. They cannot simply consume everything around them instantly. Physics itself regulates their growth rate and prevents runaway expansion that would destabilize entire galactic structures. When Andromeda collides with our galaxy, their central black holes will begin a gravitational dance that ends in cosmic catastrophe. The merger process starts when the two supermassive black holes find themselves within the same galactic system. They slowly spiral toward each other, losing orbital energy to gravitational wave radiation over billions of years. The final merger happens in seconds but releases more energy than the combined light output of 1 trillion stars. This black hole collision will create gravitational waves detectable across the entire observable universe. The resulting black hole will contain roughly 100 million solar masses, making it one of the most massive single objects in our cosmic neighborhood. This merged monster will serve as the gravitational anchor for whatever galaxy emerges from the collision of our two galactic homes. Every few years, astronomers discover new galaxies orbiting Andromeda. The count keeps climbing. Right now, scientists have confirmed several dozen of these cosmic companions. These aren't full-sized galaxies like Andromeda itself. They're much smaller systems called satellite galaxies or dwarf galaxies. Each one contains anywhere from millions to billions of stars, tiny by galactic standards. The discovery process requires incredible patience and powerful telescopes. Most satellite galaxies appear extremely faint against the background of space. They're easy to miss unless astronomers know exactly where to look. What makes this census so important is what it reveals about galaxy formation. Large galaxies like Andromeda don't grow alone. They accumulate smaller companions over billions of years. This satellite system represents a fossil record of cosmic assemblies spanning the entire age of the universe. Among all of Andromeda's companions, one galaxy stands out like a bright beacon. Astronomers call it M32, and it's unlike anything else in the satellite family. M32 appears as an elliptical galaxy, a smooth football-shaped collection of stars with no spiral arms or disk structure. What makes it remarkable is its incredible density. Stars pack together much more tightly than in typical dwarf galaxies. This compact galaxy contains roughly 3 billion stars, crushed into a space smaller than most satellite systems. If you lived on a planet orbiting a star in M32's center, your night sky would blaze with thousands of brilliant stars instead of the handful we see from Earth. Scientists believe M32 might be the stripped core of a much larger galaxy that passed too close to Andromeda. The main galaxy's powerful gravity tore away M32's outer regions, leaving only the dense central core we observe today. While M32 packs stars into a tight ball, another major satellite takes the opposite approach. M110 spreads its stellar population across enormous distances with a much more relaxed structure. This elliptical galaxy extends much farther from its center than M32, even though it contains fewer total stars. Scientists call this a diffuse galaxy, one where stars are distributed across larger volumes of space. M110's low surface brightness makes it challenging to observe. The galaxy appears as a faint, ghostly smudge that requires dark skies and sensitive equipment to detect properly. Individual stars within M110 sit much farther apart than in denser satellite systems. The difference between M32 and M110 shows how satellite galaxies can evolve along completely different paths. While one compressed into extreme density, the other expanded into a loose, extended structure spanning thousands of light years. Andromeda's massive gravity doesn't just capture smaller galaxies, it slowly destroys them. This cosmic cannibalism operates through a process called tidal disruption. Tidal forces work like the gravity that creates ocean tides on Earth, but on galactic scales. Different parts of a satellite galaxy feel slightly different gravitational pulls from Andromeda. Over millions of years, these differences stretch and tear the smaller galaxy apart. Stars get stripped away from satellite galaxies one by one. They don't disappear. Instead, they become part of Andromeda's extended halo. Long streams of stars mark the orbital paths where disrupted satellites once traveled. This process explains why many satellite galaxies appear to be missing their outer regions. Andromeda's gravity acts like a cosmic vacuum cleaner, gradually absorbing stellar material from its smaller companions. The satellite system we see today represents galaxies in various stages of this slow-motion destruction. How do tiny galaxies avoid falling directly into Andromeda's center? The answer lies in orbital mechanics, the same physics that keeps planets circling our Sun. Satellite galaxies follow elliptical orbits around Andromeda, just like comets orbiting the Sun. They swing close to the main galaxy, then arc out to great distances before returning. These orbital periods can last hundreds of millions of years. The key is maintaining the right balance between speed and distance. Move too slowly, and gravity pulls the satellite inward to destruction. Move too fast, and it escapes into intergalactic space. Most of Andromeda's satellites follow highly elongated orbits that carry them far beyond the main galaxy's visible disk. This orbital dance has continued for billions of years, creating a gravitational ballet performed on cosmic scales with participants separated by millions of light years. Open any astronomy textbook, and you'll learn that galaxies contain different generations of stars. Satellite galaxies around Andromeda showcase this principle perfectly. Most satellite stars belong to what astronomers call population 2, ancient stars that formed when the universe was young. These stellar veterans contain very small amounts of heavy elements compared to stars like our Sun. The reason traces back to cosmic history. Early in the universe, only hydrogen and helium existed. The first generation of massive stars had to create heavier elements through nuclear fusion and scatter them through space when they exploded. Satellite galaxies preserve this ancient stellar chemistry because they stopped forming new stars billions of years ago. Their stellar populations remain frozen in time, offering astronomers a window into what star formation looked like during the universe's youth. What you can see in satellite galaxies represents only a tiny fraction of what's actually there. Each small galaxy sits embedded within a much larger sphere of invisible dark matter. This dark matter halo can extend 10 times farther than the visible stars and contain 10 times more mass. The dark matter doesn't emit light, but its gravitational effects dominate how satellite galaxies behave and evolve. Without dark matter, these small stellar systems couldn't survive their encounters with Andromeda's powerful gravity. The invisible halo provides extra gravitational binding that helps hold satellite galaxies together as they orbit the main system. For astronomers, satellite galaxies offer some of the best laboratories for studying dark matter. The ratio of visible stars to invisible matter reaches extreme values in these systems, making dark matter's effects easier to detect and measure than in larger galaxies. Most satellite galaxies around Andromeda share a distinctive appearance. They look like fuzzy, round balls of stars with no internal structure or patterns. Astronomers call these dwarf spheroidal galaxies. The name describes their shape, roughly spherical distributions of stars with very low surface brightness. They lack the spiral arms, bars, or disks seen in larger galaxy systems. This spherical shape results from billions of years of gravitational stirring. Random motions of individual stars gradually erase any organized structure that might have existed originally. It's like shaking a box of marbles until they settle into a roughly round pile. The transformation from organized structure to spherical shape marks the final stage of satellite galaxy evolution. Once a system reaches this state, it can maintain its spherical form for billions of additional years, while slowly losing stars to tidal stripping. Here's what separates satellite galaxies from their larger cousins. They've completely stopped making new stars. Their stellar factories shut down billions of years ago and never restarted. The culprit is missing gas. Star formation requires cold gas clouds that can collapse under their own gravity. Satellite galaxies loss of their gas through two main processes working together. Andromeda's gravity stripped away much of the gas through tidal forces. At the same time, a process called ram pressure, like cosmic wind resistance, swept remaining gas out of the satellite systems as they moved through Andromeda's extended atmosphere. Without gas to form new stars, satellite galaxies became stellar fossils. They can only lose stars over time, never gain new ones. This explains why their stellar populations appear so uniformly old compared to galaxies that continue active star formation. Astronomers face a fundamental problem when counting Andromeda's satellites. Current telescopes can only detect the brightest members of the satellite family. Thousands of extremely faint dwarf galaxies probably orbit Andromeda completely undetected. These ultra-faint systems contain so few stars that they barely register above the background noise of space. The discovery process favors larger, brighter satellites while missing smaller, dimmer ones. It's like trying to count candles while standing next to a searchlight. You'll easily see bright flames but miss flickering birthday candles. Next-generation telescopes should reveal many more satellite galaxies around Andromeda. Computer simulations predict that hundreds or even thousands of these faint companions exist just beyond our current detection limits. The satellite census we have today represents only the tip of a much larger iceberg. Large galaxies like Andromeda didn't form all at once. They grew through a process astronomers call hierarchical formation, smaller pieces combining into larger structures over cosmic time. In the early universe, tiny proto-galaxies merged to form slightly larger systems. These medium-sized galaxies then combined to create the giants we see today. This bottom-up assembly process operated like cosmic construction on the largest scales. Today's satellite galaxies represent the leftover building blocks from this assembly process. They're the smaller pieces that haven't yet been incorporated into Andromeda's main structure. This hierarchical formation continues today at a slower pace. Andromeda gradually captures and absorbs its satellite companions, growing more massive over billions of years. The satellite system we observe provides direct evidence of how galaxies assemble themselves from smaller components throughout cosmic history. Scientists can measure the speed of something 2.5 million light-years away. That sounds impossible, but modern astronomy makes it routine. Andromeda races toward our galaxy at 110 kilometers per second. That's fast enough to circle Earth's equator in under 4 hours. This approach speed never changes. Gravity keeps pulling the two galaxies together with mathematical precision. Astronomers measure this motion using something called the Doppler effect. When objects move toward us, their light shifts slightly toward the blue end of the spectrum. When they move away, the light shifts toward red. For decades, scientists used this technique to track Andromeda's approach. The measurements all point to the same conclusion. These two galactic giants are on a collision course that nothing can prevent. The cosmic appointment was set billions of years ago by the fundamental laws of gravity. What happens when 2 trillion star galaxies collide? Until recently, nobody knew for certain. Computer simulations changed everything. Scientists can now model the entire collision process using the most powerful supercomputers on Earth. These digital experiments run the collision in fast forward, compressing billions of years into hours of computation. The results are remarkably consistent. Every simulation produces the same timeline. first approach in 4.5 billion years, followed by a complex gravitational dance lasting several billion more years. These computer models track individual star movements, gas-cloud interactions, and the behavior of dark matter halos. The simulations reveal that galactic collisions follow predictable patterns governed by gravity and orbital mechanics. What seems like cosmic chaos actually unfolds according to precise mathematical laws. Long before Andromeda and our galaxy actually merge, their gravity will start tearing both systems apart. These invisible forces operate across millions of light years of empty space. Scientists call these tidal forces, the same type of gravity that creates ocean tides on Earth, but operating on galactic scales. Different parts of each galaxy will feel slightly different gravitational pulls from the approaching neighbor. As the galaxies draw closer, these tidal forces will stretch and distort both stellar systems. Spiral arms will get pulled out of shape. Stars will be flung into new orbits. The orderly rotation that has characterized both galaxies will dissolve into chaos. The gravitational disruption begins billions of years before the galaxies actually interpenetrate. By the time the collision reaches its peak, both galactic structures will already be completely transformed from their current appearances. Here's the most counterintuitive fact about galactic collisions. Despite involving trillions of stars, almost no stars actually hit each other. The distances between individual stars are so vast that direct collisions become virtually impossible. It's like throwing two handfuls of sand at each other from opposite ends of a football stadium. The grains will pass by without touching. Instead of stellar crashes, the collision reshuffles stellar orbits on a massive scale. Stars get gravitationally kicked into new trajectories. Some get flung toward the outskirts of the merged system. Others spiral inward toward the center. This orbital reshuffling creates the most dramatic stellar migration in galactic history. Stars that spent billions of years in quiet suburban neighborhoods suddenly find themselves in completely different cosmic zip codes. The collision changes addresses without destroying homes. When the cosmic dust settles, our galaxy and Andromeda will no longer exist as separate entities. In their place will stand a single galactic giant. Astronomers have already coined a name for this future galaxy, Milkomeda. It combines Milky Way and Andromeda into a single word that represents the merged system. Milkomeda will look completely different from either parent galaxy. Instead of spiral arms and rotating disks, the merged galaxy will appear as a smooth, football-shaped elliptical galaxy. All traces of spiral structure will vanish during the collision process. This transformation follows a pattern seen throughout the universe. When spiral galaxies merge, they almost always produce elliptical galaxies. The collision destroys the delicate spiral patterns while preserving most of the stellar content in a new, more stable configuration. At the heart of this galactic collision lies an even more dramatic event. Both galaxies harbor supermassive black holes at their centers, and these cosmic monsters will eventually merge. Our galaxy's central black hole contains about 4 million solar masses. Andromeda's black hole weighs roughly 100 million solar masses. When the galaxies collide, these black holes begin a spiral dance toward each other. The merger process takes billions of years. The black holes orbit each other in tighter and tighter circles, losing energy to gravitational waves, ripples in space-time itself that carry energy away from the system. Eventually, the black holes get so close that they merge in a final catastrophic event lasting just seconds. This black hole collision will create gravitational wave so powerful they'll be detectable across the entire observable universe. The merged black hole will become the gravitational anchor of the new Milky galaxy. Galactic collisions don't just rearrange existing stars. They trigger the largest star formation events in the universe. When gas clouds from both galaxies crash into each other, they compress to incredible densities. This compression provides exactly the conditions needed for massive star formation bursts that can last hundreds of millions of years. The collision will produce more new stars than both galaxies have created in the previous billion years combined. These stellar nurseries will blaze with the light of millions of newborn stars forming simultaneously across the merged system. Scientists call this a starburst event, a period when star formation rates increase by factors of 10 or even 100 above normal levels. These cosmic construction booms reshape galactic chemical evolution and create some of the most spectacular light displays the universe offers. What happens to Earth during this cosmic collision? The answer might surprise you. Computer simulations suggest our solar system has excellent survival prospects. The Sun and its planets will likely get kicked into a new orbit within the merged galaxy, but the gravitational bonds holding our planetary system together should remain intact. 2. Our new galactic address will probably be somewhere in the outer suburbs of Andromeda. The solar system might end up much farther from the galactic center than it is today, in a quieter region with fewer stellar neighbors. The collision timeline works in our favor. 4.5 billion years from now, the Sun will be nearing the end of its main sequence lifetime anyway. By the time the galactic merger peaks, our solar system will already be dealing with the Sun's evolution toward red giant phase. The collision becomes just one more factor in our cosmic future. When those two supermassive black holes finally merge, they'll create the most powerful gravitational wave signal in our cosmic neighborhood's history. Gravitational waves are ripples in space-time itself, distortions that travel at the speed of light and carry information about the most violent events in the universe. Einstein predicted their existence, but scientists only detected them recently. The black hole merger at Milky's heart will generate gravitational waves billions of times stronger than any signal detected so far. These space-time ripples will race outward from the collision site, carrying energy equal to the annihilation of several solar masses. Future gravitational wave detectors will observe this merger from billions of light years away. The signal will provide unprecedented insights into black hole physics and the final stages of galactic evolution. This cosmic announcement will mark the completion of the largest gravitational structure formation event in our local universe's history. The end result of this cosmic collision will be a galaxy unlike anything we see today. Andromeda will have no spiral arms, no rotating disk, and no organized structure. Elliptical galaxies dominate the universe's most massive galaxy clusters. They represent the final evolutionary stage for galactic systems. Stable, long-lived structures that resist further major changes. Andromeda will join the ranks of these galactic giants. The merged system will be roughly spherical, filled with stars following chaotic orbits around the central supermassive black hole. All memory of spiral organization will be erased. This transformation marks the end of an era in our local universe's evolution. The beautiful spiral patterns that have characterized both parent galaxies for billions of years will vanish forever. In their place will stand a monument to gravity's ultimate victory, a stable elliptical galaxy that could persist virtually unchanged for the rest of cosmic time. Why do stars in different parts of Andromeda contain different mixtures of chemical elements? The answer lies written in their light. When astronomers analyze starlight from various regions of the galaxy, they discover a clear pattern. Stars near the center contain much higher concentrations of heavy elements than stars in the outer regions. Scientists call this a metallicity gradient. In astronomy, metals means any element heavier than hydrogen and helium, things like carbon, oxygen, iron, and gold that we consider normal matter. This chemical map tells the story of how galaxies build up their element inventory over billions of years. The center of Andromeda processed more stellar generations than the edges, creating the chemical gradient we observe today. Heavy elements concentrate where star formation operated most efficiently throughout cosmic history. Not all stars in Andromeda were born at the same time or in the same way. Astronomers have discovered two distinct stellar families living in separate galactic neighborhoods. Population-I stars are the young, metal-rich residents of spiral arms and the galactic disk. They contain substantial amounts of heavy elements forged by previous stellar generations. Population-I stars are ancient, metal-poor veterans that populate the galactic halo and central bulge. These stellar populations formed during different eras of galactic evolution. Population-I stars represent the first major wave of star formation when the galaxy was young and chemically primitive. Population-I stars formed later from gas enriched by countless stellar deaths. The spatial separation of these populations reflects Andromeda's chemical evolution over cosmic time. Young, metal-rich stars cluster where ongoing star formation continues processing heavy elements. Old, metal-poor stars occupy regions where star formation ended billions of years ago and chemical evolution essentially froze in place. How did the universe create the 90-plus elements we find in nature? The answer lies in the nuclear furnaces burning inside stars throughout Andromeda's history. When stars form, they start with mostly hydrogen and helium left over from the Big Bang. Nuclear fusion in stellar cores slowly builds heavier elements by combining lighter ones. Hydrogen fuses to make helium. Helium fuses to create carbon and oxygen. The process continues up the periodic table. Different types of stars create different elements. Massive stars forge elements up to iron through successive fusion reactions in their cores. Stars like our Sun produce carbon and nitrogen during their final evolutionary phases. This nucleosynthesis process has operated throughout Andromeda's billion-year history. Each stellar generation inherited the chemical legacy of its predecessors and added new elements to the galactic inventory. The cumulative result is the rich chemical diversity we observe in modern stellar populations across the galaxy. When the most massive stars die, they don't fade quietly into cosmic darkness. They explode with enough violence to scatter heavy elements across entire galactic neighborhoods. Supernovae represent the primary factories for iron peak elements: iron, nickel, cobalt, and similar metals that form the cores of rocky planets. These stellar explosions create extreme temperatures and pressures that forge elements impossible to produce during normal stellar burning. The explosion blasts these newly created elements into surrounding space at thousands of kilometers per second. Shock waves from supernovae enrich the interstellar medium with heavy elements that future stellar generations will incorporate. In Andromeda, supernova enrichment has operated for billions of years, gradually increasing the metal content of star-forming regions. The frequency and distribution of these explosions shaped the galaxy's chemical evolution patterns and determined where heavy elements concentrate most effectively. Not all stellar chemical processing happens through violent explosions. Some of the most important element production occurs during the quiet death throes of medium-mass stars. When stars between 1 and 8 solar masses reach the end of their lives, they enter a phase called the asymptotic giant branch. During this period, they puff off their outer layers in gentle stellar winds that carry freshly made elements into space. These dying stars specialize in producing carbon and nitrogen through nuclear processes in their cores. They also create small amounts of heavier elements through neutron capture reactions that occur in their extended atmospheres. GB stars contributed significantly to Andromeda's chemical evolution by enriching the galaxy with these intermediate mass elements. Their gentle element dispersal operates continuously across billions of years, providing a steady supply of carbon and nitrogen for future stellar and planetary formation. Here's a fundamental rule of galactic chemistry. Older stars contain fewer heavy elements than younger stars. This age-metallicity relationship tells the story of how galaxies chemically evolve over time. Stars that formed early in Andromeda's history had only the primordial hydrogen and helium to work with. As successive generations of stars lived and died, they gradually enriched the galaxy's gas supply with heavier elements. Each new generation of stars inherited this accumulated chemical wealth. Stars forming today incorporate elements created by billions of years of stellar nucleosynthesis and supernova explosions throughout the galaxy's history. The age-metallicity relationship provides astronomers with a cosmic clock. By measuring a star's heavy element content, they can estimate approximately when it formed during the galaxy's chemical evolution. This technique reveals the timeline of star formation and chemical processing throughout Andromeda's billion-year history. Astronomers discovered something puzzling when they counted stars of different metallicities in our own galaxy. They found too few metal-poor stars compared to theoretical predictions. This puzzle became known as the G-dwarf problem. Computer models of galactic chemical evolution predict that many more low metallicity stars should exist than observations actually detect. The same pattern appears in Andromeda and other nearby galaxies. Several solutions could explain this discrepancy. Perhaps low metallicity stars formed less efficiently than models assume. Maybe metal-poor stars have shorter lifespans than expected. External gas infall could also dilute the number of metal-poor stars relative to metal-rich ones. The G-dwarf problem highlights gaps in our understanding of how galaxies chemically evolve. Solving this puzzle requires better models of star formation efficiency, stellar lifetimes, and gas flow patterns during the early phases of galactic evolution. Galaxies don't evolve as closed chemical systems. Throughout their histories, they continue accreting fresh gas from the surrounding intergalactic medium. This external gas infall brings primordial material, mostly hydrogen and helium with very low heavy element content, into the galaxy. The infalling gas mixes with chemically enriched material already present, diluting the overall metallicity. Gas infall helps explain several puzzles in galactic chemical evolution. It accounts for the G-dwarf problem by reducing the number of very metal-poor stars. It also explains how galaxies maintain star formation for billions of years without exhausting their gas supplies. In Andromeda, gas infall has operated throughout the galaxy's history, providing fresh fuel for continued star formation while moderating the pace of chemical enrichment. This external supply ensures that chemical evolution proceeds gradually rather than reaching extreme metallicities quickly. Some of the most important chemical enrichment in Andromeda comes from a specific type of stellar explosion involving binary star systems. Type I supernovae occur when a white dwarf star, the dense remnant of a Sun-like star, accumulates material from a companion star. When the white dwarf reaches a critical mass, it explodes completely in a nuclear detonation. These explosions produce large quantities of iron and nickel while creating very little of the lighter elements made by massive star supernovae. Type I events provide a distinct chemical signature that astronomers can track throughout galactic evolution. The frequency of Type I supernova depends on the formation rate and evolution timescales of binary star systems. In Andromeda, these explosions have contributed significantly to the galaxy's iron inventory, especially in regions where intermediate-age stellar populations dominate the chemical evolution history. How do elements created in stellar cores end up distributed evenly throughout galactic neighborhoods? The answer involves several mixing processes operating on different scales. Turbulence in the interstellar medium stirs newly ejected elements with pre-existing gas. Stellar winds and supernova shock waves create bubbles and cavities that promote large-scale mixing. Galactic rotation and spiral density waves help redistribute material across vast distances. These mixing processes operate over millions of years, gradually homogenizing the chemical composition of star-forming regions. Without efficient mixing, newly created elements would remain concentrated near their stellar sources. In Andromeda, chemical homogenization has operated throughout the galaxy's history, ensuring that star-forming regions maintain relatively uniform compositions despite the localized nature of element production. This mixing enables the smooth metallicity gradients observed across the galactic disk. When Andromeda collides with our galaxy in 4.5 billion years, their distinct chemical evolution histories will merge into something completely new. Each galaxy developed its own metallicity gradients, stellar population distributions, and element abundance patterns over billions of years of independent evolution. The collision will mix these separate chemical histories together. Gas clouds from both galaxies will collide and merge, creating hybrid compositions unlike anything in either parent system. Star formation bursts during the collision will incorporate this mixed material into new stellar generations. The merged galaxy will eventually establish new chemical evolution patterns based on its combined stellar populations and gas reservoirs. This cosmic blend will erase the individual chemical signatures of both parent galaxies, creating a fresh start for galactic chemical evolution in the merged Milky Way system. Stars in Andromeda's outer regions move too fast. According to the laws of physics, they should be moving much slower or flying off into space completely. When astronomers measure how fast stars orbit in different parts of the galaxy, they discover something impossible. Stars far from the center maintain nearly the same speeds as stars closer in. This violates everything we know about orbital mechanics. Scientists call this a flat rotation curve. In our solar system, outer planets orbit much slower than inner planets because the sun's gravity weakens with distance. Galaxies should work the same way, but they don't. The only explanation is that invisible matter fills the galaxy. This dark matter provides extra gravitational pull that keeps outer stars moving at high speeds. Without this unseen mass, Andromeda's outer regions would have dispersed into space billions of years ago. The rotation curve proves that what we can't see controls what we can. What you can see in Andromeda represents only a small fraction of what's actually there. The visible galaxy floats within a much larger sphere of invisible dark matter. This dark matter halo contains 5 times more mass than all the stars, gas, and dust combined. If you could see dark matter, Andromeda would appear as an enormous ghostly sphere extending far beyond the spiral arms we observe in photographs. The dark matter doesn't interact with light in any way. It doesn't emit, absorb, or reflect electromagnetic radiation. Scientists know it exists only through its gravitational effects on visible matter. For Andromeda, this invisible mass provides the gravitational foundation that holds the entire galaxy together. The dark matter halo determines the galaxy's total gravitational field and shapes how visible matter behaves throughout the system. Everything we can observe operates within the gravitational architecture created by this unseen empire. Dark matter doesn't spread evenly throughout Andromeda's halo. Instead, it follows a precise mathematical pattern that astronomers can measure indirectly. The density of dark matter decreases predictably as you move away from the galactic center. Scientists describe this using power law relationships, mathematical formulas where density drops according to specific exponential rules. This density pattern emerged from computer simulations of how dark matter behaves under gravity alone. The simulations consistently produce the same result. Dark matter naturally organizes itself into dense central concentrations surrounded by more diffuse outer regions. In Andromeda, this density distribution shapes how the galaxy's gravitational field varies with location. The mathematical precision of this pattern suggests that dark matter follows well-understood physical laws, even though we can't observe the particles directly. Sometimes the best way to study something invisible is to watch how it bends light from objects behind it. Dark matter creates these cosmic magnifying glass effects throughout Andromeda. When light from distant background galaxies passes near massive dark matter concentrations, it gets deflected slightly from its straight-line path. This gravitational lensing creates distorted images that astronomers can measure with sensitive telescopes. Scientists call this weak lensing because the distortions are subtle, typically less than 1% changes in galaxy shapes. But by analyzing thousands of background galaxies, astronomers can map how dark matter distributes throughout Andromeda's halo. The lensing technique provides the most direct way to study dark matter's spatial distribution. It reveals clumps, streams, and substructures within the dark matter halo that would be completely invisible otherwise. These gravitational maps show dark matter's role in shaping galactic architecture. Dark matter doesn't form one smooth, uniform halo around Andromeda. Instead, it organizes into a complex hierarchy of smaller structures nested within larger ones. Computer simulations predict that thousands of small dark matter clumps orbit within Andromeda's main halo. Scientists call these subhalos, dense concentrations of dark matter that survived the galaxy formation process. Most subhalos contain no visible stars or gas. They exist as purely dark matter structures that interact with the main galaxy only through gravity. Some subhalos may host the small satellite galaxies we can observe around Andromeda. This subhalo structure reflects how galaxies form through hierarchical assembly. Large dark matter halos grow by capturing and merging with smaller ones. The subhalos represent partially digested remnants of this cosmic construction process that continues operating today. When satellite galaxies orbit through Andromeda's dark matter halo, they experience a kind of cosmic friction that gradually changes their paths. This dynamical friction doesn't involve physical rubbing like mechanical friction. Instead, it results from gravitational interactions between the satellite and dark matter particles in the halo. As a satellite moves through the dark matter, it creates a gravitational wake behind it, similar to how a boat creates waves in water. This wake exerts a drag force that slowly removes orbital energy from the satellite system. Over hundreds of millions of years, dynamical friction causes satellite galaxies to spiral inward toward Andromeda's center. This process helps explain why we observe fewer massive satellites than computer simulations predict. Many have already been consumed through this cosmic friction mechanism. Andromeda's powerful gravity doesn't just capture satellite galaxies. It gradually tears away their dark matter halos piece by piece. This tidal stripping operates through the same gravitational forces that create ocean tides, but on galactic scales. Different parts of a satellite's dark matter halo experience slightly different gravitational pulls from the main galaxy. Over cosmic time, these tidal forces strip away the outer layers of satellite dark matter halos. The process continues until only the dense central cores remain bound to the satellite galaxies. Tidal stripping explains why satellite galaxies appear to have much less dark matter than isolated galaxies of similar size. Most of their original dark matter halos have been gradually removed and incorporated into Andromeda's extended halo structure. What exactly is dark matter made of? Despite decades of research, scientists still don't know the answer. The leading candidates include exotic particles that barely interact with ordinary matter. WIMPs, weakly interacting massive particles, represent one popular possibility. These hypothetical particles would have mass but interact only through gravity and the weak nuclear force. Another candidate is the action, an extremely light particle predicted by certain theories of particle physics. Actions would be produced in enormous quantities but remain nearly undetectable because they interact so weakly with normal matter. Scientists around the world are building increasingly sensitive detectors to search for these mystery particles. Dark matter research represents one of the biggest unsolved problems in modern physics, with profound implications for our understanding of the universe's fundamental composition. Deep beneath the Earth's surface, scientists operate some of the most sensitive particle detectors ever built. They're hunting for direct evidence of dark matter particles. These underground laboratories shield detectors from cosmic rays and other background radiation that could create false signals. The experiments wait for dark matter particles to collide with atomic nuclei in specially prepared target materials. A successful detection would register as a tiny amount of energy deposited when a dark matter particle strikes a nucleus. But these collisions are extremely rare, maybe 1 or 2 events per year in a detector containing tons of material. Despite decades of increasingly sensitive searches, no experiment has definitively detected dark matter particles yet. Each negative result constrains the possible properties of dark matter and guides the design of even more sensitive future experiments. If dark matter particles can destroy each other through mutual annihilation, they might produce detectable radiation that telescopes could observe. When 2 dark matter particles collide and annihilate, they could create gamma rays, neutrinos, or other forms of radiation. These annihilation products would carry unique energy signatures that could identify them as dark matter signals. Scientists search for these indirect signals using spaced gamma-ray telescopes and neutrino detectors. They look for excess radiation coming from regions where dark matter concentrations should be highest, like galactic centers or dark matter clumps. So far, indirect detection experiments have found several intriguing signals, but none have been confirmed as definitive dark matter discoveries. The search continues with increasingly sophisticated instruments designed to distinguish dark matter signals from conventional astrophysical sources. Computer simulations and astronomical observations disagree about how dark matter behaves in galactic centers. This discrepancy has puzzled scientists for decades. Simulations predict that dark matter density should increase sharply toward the center of galaxy halos, creating what scientists call a cusp. But observations suggest that many galaxies have relatively flat central density profiles called cores. This cusp core problem might indicate that our understanding of dark matter is incomplete. Perhaps dark matter particles interact with each other more strongly than current theories predict. Or maybe normal matter affects dark matter distribution in ways we haven't considered. Alternative explanations include modified gravity theories that eliminate the need for dark matter entirely. Resolving this controversy requires better observations of galactic centers and more sophisticated computer simulations that include the complex physics of star formation and galactic evolution. When Andromeda collides with our galaxy, their dark matter halos will merge to create the most massive gravitational structure in our cosmic neighborhood. The dark matter collision will happen differently from the stellar collision. Dark matter particles can pass through each other without direct interactions, so the two halos will interpenetrate and gradually merge through gravitational forces alone. Computer simulations show that the merged dark matter halo will be significantly more massive than either parent system. The combined structure will dominate the gravitational dynamics of our entire local galactic group. This dark matter merger will reshape the cosmic architecture of our region of the universe. The new halo will capture additional satellite galaxies, organize local galactic motions, and provide the gravitational foundation for whatever stellar system emerges from the galactic collision. High above Earth's atmosphere, a telescope the size of a school bus peers deep into Andromeda with unprecedented clarity. The Hubble Space Telescope can distinguish individual stars in a galaxy 2.5 million light-years away. This capability revolutionized our understanding of galactic structure and stellar evolution. Before Hubble, Andromeda appeared as a smooth spiral of blended starlight. Now astronomers can study individual red giants, star clusters, and stellar neighborhoods with the same detail possible in our own galaxy. Hubble's resolution comes from operating in the vacuum of space, where Earth's turbulent atmosphere can't blur the images. The telescope can separate stars that appear less than 1/10,000th of a degree apart in the sky. For Andromeda research, this individual star resolution provides the foundation for measuring distances, ages, and chemical compositions throughout the galaxy. Hubble transforms a distant spiral nebula into a detailed stellar census that reveals how galaxies build their populations over cosmic time. Cosmic dust blocks visible light throughout Andromeda's disk, hiding much of the galaxy's star formation activity from optical telescopes. The James Webb Space Telescope solves this problem by observing in infrared light. Infrared radiation passes through dust clouds that completely block visible light. This allows Webb to peer inside the dense molecular clouds where new stars form and study regions of the galaxy previously hidden from view. Webb's infrared detectors are so sensitive they can detect the heat glow from individual forming stars embedded within thick dust cocoons. The telescope reveals star formation happening in real time across Andromeda's spiral arms. This infrared capability also detects the cold gas reservoirs that fuel future star formation. Webb maps the distribution of molecular hydrogen, the raw material for stellar birth, throughout regions where optical telescopes see only dark patches. For studying galactic evolution, infrared vision provides access to the hidden half of Andromeda's stellar production process. Can astronomers measure the tiny motions of individual stars in a galaxy millions of light years away? The European Gaia satellite makes this incredible feat possible for Andromeda's brightest stellar residents. Gaia operates like a cosmic surveyor, measuring stellar positions with accuracy better than the width of a human hair seen from 1,000 kilometers away. Over multiple years of observations, the satellite can detect the minute changes in stellar positions caused by orbital motion. These proper motion measurements, the sideways movement of stars across the sky, reveal how Andromeda's stellar populations move within the galaxy's gravitational field. Scientists can track individual star clusters and stellar streams created by past galactic interactions. For Andromeda, Gaia's precision measurements provide the first direct observations of internal galactic dynamics in an external galaxy. These motion studies reveal dark matter distribution, measure galactic rotation patterns, and trace the orbital histories of stellar populations across cosmic time. Most of the matter in Andromeda doesn't shine with visible light. Radio telescopes detect this invisible material by observing the faint signals emitted by cold hydrogen gas. Radio interferometry connects multiple telescopes across continents to create virtual instruments with incredible resolution. These arrays can map the distribution and motion of hydrogen gas throughout Andromeda's disk with detail comparable to optical images. The 21-centimeter radio line, emitted when hydrogen atoms flip their magnetic orientation, provides the primary tool for studying galactic gas dynamics. This radiation passes through dust without absorption, revealing the complete three-dimensional structure of Andromeda's gas reservoirs. Radio mapping reveals how gas flows through spiral arms, where it accumulates to form new stars, and how stellar feedback drives material back into intergalactic space. These observations provide the missing piece needed to understand how galaxies regulate their star formation over cosmic time. Some processes in Andromeda generate temperatures of millions of degrees, far too hot to emit visible light. X-ray telescopes detect these extreme cosmic phenomena that remain invisible to other instruments. X-ray emission traces the most energetic events in galactic evolution: supernova explosions, stellar mass black holes consuming matter, and hot gas heated by stellar winds and supernova shock waves. Space-based X-ray observatories like Chandra and SXMM Newton map these high-energy phenomena throughout Andromeda's structure. They reveal how stellar death and stellar birth create feedback loops that regulate galactic evolution. X-ray observations also detect the hot gaseous halos surrounding galaxies, material heated to such high temperatures that it glows only in X-rays. These observations trace how galaxies exchange matter with their cosmic environments and how supermassive black holes influence their host galaxies across cosmic distances. If dark matter particles can destroy each other through annihilation, they might produce gamma rays, the highest energy form of electromagnetic radiation. Space-based detectors search for these cosmic signals throughout Andromeda. Gamma-ray telescopes scan for excess radiation coming from regions where dark matter should concentrate most densely. They look for energy signatures that match theoretical predictions of dark matter particle interactions. The Fermi Gamma Ray Space Telescope monitors the entire sky continuously, searching for the telltale signals that could finally reveal dark matter's true nature. These observations could solve one of the biggest mysteries in modern physics. Beyond dark matter searches, gamma-ray astronomy studies the most violent processes in the universe. It detects high-energy particle acceleration in stellar explosions, neutron star collisions, and other extreme events that shape galactic evolution throughout cosmic history. Ground-based astronomy is preparing for a revolution. Telescopes with mirrors 30 meters across, larger than basketball courts, will provide unprecedented detail about Andromeda's stellar populations. These extremely large telescopes will collect enough light to obtain detailed spectra from individual stars in Andromeda. Spectroscopy reveals stellar temperatures, chemical compositions, ages, and masses by analyzing the specific wavelengths of light each star emits. Current telescopes can only study the brightest individual stars in external galaxies. The new generation will extend detailed spectroscopic analysis to ordinary stars throughout Andromeda's disk and halo populations. This capability will transform our understanding of galactic chemical evolution by providing individual stellar measurements across entire galactic populations. Astronomers will trace element production and distribution with the same detail currently possible only in our immediate galactic neighborhood. When Andromeda's central black hole eventually merges with our galaxy's central black hole, it will create the most powerful gravitational wave signal in our cosmic neighborhood's history. Future space-based gravitational wave detectors will monitor these cosmic collisions from millions of light-years away. Unlike ground-based detectors that observe stellar mass black holes, space interferometers will track supermassive black hole mergers. The Laser Interferometer Space Antenna, LISA, represents the first of these space-based detectors. It will use 3 spacecraft separated by millions of kilometers to detect the space-time ripples created by massive black hole collisions. These gravitational wave observations will provide completely new information about how supermassive black holes form and merge throughout cosmic history. They offer the only direct way to study black hole physics during the most extreme gravitational events the universe produces. Professional astronomers cannot analyze the millions of images and data sets generated by modern telescopes. Citizen science projects recruit public volunteers to help process this cosmic information overload. Galaxy Zoo represents the most successful example of this collaboration. Volunteers examine telescope images and classify galactic structures, star formation regions, and unusual features that automated systems might miss. Hundreds of thousands of citizen scientists have contributed to our understanding of galactic evolution by identifying spiral patterns, merger signatures, and stellar populations throughout thousands of galaxies, including Andromeda. These public participation projects demonstrate how scientific research benefits from distributed human intelligence. Pattern recognition tasks that challenge computers become manageable when distributed among motivated volunteers who contribute their visual processing skills to advance astronomical understanding. Modern astronomical surveys generate more data than human researchers can analyze in lifetimes. Artificial intelligence systems now help astronomers discover patterns and relationships hidden within these massive datasets. Machine learning algorithms can identify stellar populations, classify star formation regions, and detect unusual objects throughout Andromeda's structure. These AI systems process thousands of images simultaneously, finding patterns that would take human astronomers decades to recognize. Neural networks trained on astronomical data can predict stellar properties, identify galaxy merger signatures, and even discover new types of cosmic phenomena by recognizing subtle patterns in observational data. For Andromeda research, machine learning accelerates the pace of discovery by automating routine analysis tasks and highlighting unusual features that deserve detailed study. These AI systems serve as tireless research assistants that never need sleep and can process information at inhuman speeds.